Welcome everyone. Let's go ahead and take a look at another example which requires the use of the method of variation of parameters. So I hope you have seen that lesson in your differential equation class. Let me give you a recall of those formulas. So we know for the method of variation of parameters, we use the following formula to get our general solution. So we know the general solution y is going to be u times y1 plus v times y2, where y1 and y2 are the solution of the corresponding homogeneous equation. And here we know that u is given as negative integral of g times y2 over the Wronskian dt, or dx if x is your independent variable. And the formula to determine b would be the integral of g times y1 over the Wronskian dt. So hopefully you have seen that already, the derivations. Some textbooks might use different notation, but eventually you get to the same answer. So some books might use u1 and u2 for my notation of u and v. Okay, so let's see why we're going to use this method. Because as you can see, the right side of the equation, we have a function of t, and it's e to the t divided by 1 plus t squared, which happens to be on the bottom, so it's considered rational. So we know the undetermined coefficients method is not going to be useful. So we go with this method. Let's go ahead and first compute the corresponding solution to the corresponding homogeneous equation. So our homogeneous equation is y double prime minus 2y prime plus y equal to 0. You simply set the right-hand side to 0. Now we're going to assume the solution to this differential equation is y equals e to the RT. Now, once you assume that you take its first derivative, second derivative, plug everything back into this corresponding homogeneous, you're going to get the characteristic polynomial, which will look like r squared minus 2r plus 1 equals to 0. Now we're going to try to factor this, find the roots of this characteristic polynomial equation. So I'm going to go ahead and try to factor. Looks like this can be factored into r minus 1 times r minus 1, which really is just r minus 1 squared equals 0. That means we have repeated real roots. R1 is exactly equal to R2, which is 1. What that means is our solution to the homogeneous looks like this. Will be some constant C1, e to the r is 1, so t plus C2 times t e to the R2, which is also t. So make sure you know how to do this part. All right, now that we got the homogeneous solution, now since our formulas requires y1 and y2, I'm going to go ahead and label them from here. So I'm going to go ahead and label this function to be my y1 and this function to be my y2. Now I'm going to go ahead and compute the Wronskian. This is the second step. The Wronskian of the two solution, y1 and y2, is simply equal to this determinant matrix, y1, y1 prime, y2, y2 prime. And you're going to put them accordingly and compute the determinant of this matrix. So let's go ahead and substitute them as I have labeled. Y1 is e to the t. Its derivative is also e to the t. We're differentiating respect to t. Y2, I labeled it as t, e to the t. Here, when you differentiate, you use the product rule. Derivative of t respect to t is 1. So you have 1 e to the t plus t, and then derivative of e to the t is e to the t. All right, so that is our setup for this matrix. Now we multiply this times that. So that's going to give us e to the t times e to the t, that's e to the 2t, plus, and then t e to the 2t by distribution. And then we subtract the product of these guys, which will be minus t e to the 2t. And here, as you can see, these guys will cancel out. Our Wronskian comes out to be e to the 2t. All right, so let's hold on to that. That's going to be used up in our formulas for determining u and v. Now, the third step is to find the formulas u. So u is going to be negative the integral of g times y2 over the Wronskian respect to t. Let's go ahead and substitute g and y2. So we have the integral negative. So g is going to be this function right here. Then we know y2. Y2 we said is this one right here, and the Wronskian is right here. Let's go ahead and substitute them. So you'll have g, which is e to the t, divided by 1 plus t squared, and then times y2. Y2 is, as we labeled, that's t, e to the t, and divided by the Wronskian. The Wronskian is e to the 2t dt. All right, so that's how it looks like. Now let's go ahead and simplify. Now, by laws of exponents, this is e to the 2t, which cancels with this one. Then you simply integrating the following, the negative t over 1 plus t squared dt. Now, that's a very nice integral to work out. You can do a u substitution. That's what I'm going to do. Let u to be the denominator, 1 plus t squared. Then we know du, oh, I'm sorry, what am I doing u? It is u substitution, but I think I don't want to use u again. I already used that for the formula. Let me do a w substitution so we don't get confused with the variables. W is equal to 1 plus t squared. Then dw is equal to 2t dt. I already have t dt, I divide by 2. So I have 1/2 dw would replace t dt. All right, so then my integrand can be replaced in the w variable. This would be negative 1/2 the integral of 1 over w dw. All right, so this will give us negative 1/2 ln of absolute value of w plus some constant c1. Now, what is w? Well, that's simply 1 plus t squared. Now, since t squared will always give you positive value, you can remove the absolute values. So this is simply negative 1/2 ln of 1 plus t squared plus some constant c1. All right, let's hold on to that. That is the formula for u. We need to compute one more formula, which is v. So let's go ahead and do that. So we know v, it's going to be the integral of g times y1 over the Wronskian dt. This will be the integral. So g of t, we know it's e to the t over 1 plus t squared. Y1, let's see what y1 was. Y1, we labeled that as this guy right here, e to the t, and the Wronskian is e to the 2t. All right, so we have e to the t, and then divided by e to the 2t, and respect to dt, respect to t. All right, now again, these guys combines to e to the 2t, and then it cancels with that. So we're simply integrating 1 over 1 plus t squared dt. Now that is a very popular integral from calculus. You should know this is the arctangent or tangent inverse of t plus some constant c2. All right, not so bad. That is our formula for v. Now we're going to generate our general solution. So our general solution, it's going to be y equals u times y1 plus v times y2. So u is, let's see, so u is right here. That's going to be the negative 1/2 ln of 1 plus t squared plus c1. I'm going to put that right here. That's my u multiplied by y1. Y1 was e to the t plus v. Well, v is this function plus the constant c2. I'm going to put that right here. Let me get myself some room. Okay. And then this will get a multiplication of y2, which happens to be t e to the 2t. That was from the homogeneous solution. Okay, so let me just take you back to show you what I got it from. Right here, here's y1, here's y2. All right, so finishing it off by distribution. So this is C1. Distribute these out, distribute this out. Now note that when you distribute the C1 times the function C2 times that function, those are the pieces from your homogeneous. So I'm going to write them out towards the end. So my solution should look like this, negative 1/2 ln of, let me write the exponential first, 1/2 e to the t ln of 1 plus t squared plus, now I'm going to go ahead and distribute this guy out. So that will give you t e to the t tangent inverse of t. Then I have the homogeneous solution. That will be the C1 with the function e to the t plus C2T e to the T. That is your general solution, and they're all unique terms. So just to emphasize a little bit more about this solution, this is what we call Y sub H, the homogeneous solution. And the remaining pieces, which is these guys, that will be the particular solution. We call it YP. I hope this method makes sense. Take care, everyone.